Okay, so we got chapter 4 here, and that's protein methods. This is kind of a newish thing that I didn't usually cover a whole lot of before because most people are medical, but I feel like more people are going towards more, this has become more important. Let's put it that way. And medical people are seeing this more, okay? And so this is part of the reason I'm pressured on trying to get all this stuff in. Okay, so proteins can be purified, of course. This can be performed by subjecting an impure mixture of starting material to a series of separations. These will be based typically on physical properties such as size and charge. They will require a test or assay that determines whether the protein of interest is present. You all know this already because I've actually made you guys do a lot of this stuff in like organic chemistry and stuff, right? Just keep in mind that the organic chemistry stuff is very small molecules compared to this. What happens when you get bigger molecules? First off, let me ask you something. If a raindrop drops and hits concrete, does a chemical reaction occur? Yes. Yeah, actually. It has a pretty good chance of occurring. It'll only happen to a little bit of the water, so most of it doesn't. But that actually can generate hydroxyl free radicals, okay? So if you're doing something that's very big, okay, you're handling a little marble. How likely is it you're going to break it? Not very, right? Well, that's what starts happening as the thing gets bigger and bigger and bigger, and is made out of the same material. Okay, I can pick up the desk, which is made out of actually the building is made out of stronger material than the desk, right? The desk doesn't break when I pick it up, though, does it? What happens if I try to pick the building up? It'll snap, won't it? Okay? And so when I work with proteins, you have to be really careful, okay? There's a very high chance if you try to do the stuff that you would do on a organic system, small molecule system, where we're like boiling solvents off and stuff, you're going to destroy those damn proteins, okay? That acid-base separation still would work with a protein, but if you do those acid-base shifts like you did with the molecules in organic chemistry, you're not going to have that protein at the end, okay? You'll destroy it instead. Right? So keep in mind, there's a whole difference. It's a difference in steps, just small differences, but when you get something so big, it really adds up, okay? Okay, so an assay of an enzyme lactate dehydrogenase detects NADH spectrophotometrically. They could have just said spectroscopically, but whatever. Really went for the long one there. The lactate here, and here's the NAD+. This is the lactate dehydrogenase. And then we have here the NADH right here. And so you can actually detect this species very easily using a spectroscopic technique, okay? So to analyze how a purification scheme is working, the amount of total protein present in the mixture being assayed has to be known. The specific activity is going to equal the ratio of the enzyme activity to the amount of protein in the mixture. Basically, what you look at when you assay proteins is typically you don't look for the amount of protein, okay? And that's because proteins are all kind of alike, and the fragment of the protein would be basically the same as the protein, right? If you were to try to look for those. It have the same functional groups, it'd be a pain in the ass. Not really doable on any consistent, quick matter, okay? And so what you look at is you would take the total amount of protein, you have an idea of what the activity for that would be, how much it would bind something, how much it would convert something, how much it would take NAD plus and convert it to NADH, right? And so what you can do is you can time that reaction, see how long it takes to convert a specific amount of NADH, and however long that takes, that tells you how much of the protein you have, doesn't it? As long as you know how much you should have started with. Okay? Well, it does tell you how much of the protein you have, period, but not in a very precise way. Okay? If you know how much you have, it much better precision. Or at least have an idea. The overall goal of the purification is going to be to maximize that specific activity. Specific activity, again, being the ratio of the enzyme activity to the amount of protein in the mixture. Okay? Now, please do note the use of enzyme and protein here. Do I have to know that enzyme amount in the mixture? No, just protein, right? Yeah, that's all I'm looking for. Okay, so what are we going to do to release a protein from a cell? You've actually probably done this to some degree. Have you guys done a protein extraction? Or a cell extraction? Yeah? Okay, so you've kind of done something like this. Close enough, okay? Like you have an idea. Yeah. So step one is going to be disrupting the cell membranes of your intact cells to form a homogenate. What is a homogenate? Same throughout, right? Yeah. If you have them in the cells, you just get the cell. You can't do anything, right? So you got to destroy the cell, but you have to destroy it in a way that you're not going to destroy everything else, right? Okay. So that's actually, like every single one of these steps, I'm going to summarize them into very short things, but yeah, every one of them has complexity to it. Step two would be to centrifuge the homogenate at a low speed. This will yield a pellet consisting of heavy material and light supernatant. So you'll get really big things like your cell membrane if it mostly stayed together. DNA can come out if you spin it too high. You can modulate how fast you spin it. Faster you spin it, the smaller the things that will come out in the pellet. Okay? This is why they have the high-speed ones, by the way, in the downstairs, where we have much lower speed ones. You could do the low-speed ones we have for the initial heavy stuff, but the lighter stuff you wouldn't be able to get out with what we have. Step three is to centrifuge the supernatant at a high centrifugal force to yield another pellet and another additional supernatant. There will still be components in the supernatant. That's why it's called supernatant. It's not just water. Okay? But you'll get another pellet that has other things in it. Okay? At this point, this is typically your stuff like your DNA. Your proteins are almost certainly kind of coming out by this point. So this process of your differential centrifugation is going to be repeated as many times as you need. This will yield you several fractions that will decrease in density each time. Now, keep in mind, it's not just pure molecular weight that determines what comes out. Okay? It's the density versus how well it interacts with the solution, right? But if you do this very carefully, just ramping up the speed each time, you can separate things with fairly little difference in them, okay? To give you an idea of the extremes that this can get, you can separate different isotopes from each other by taking a centrifuge that's the size of a football field, okay? The process, one fraction is going to be enriched for the desired activity. You would literally take these different pellets, take them out, re-dissolve them, and then put in the reactant that you can monitor with anything else that needs to accompany it to do the reaction. And then you can see which ones do the reaction and have activity. Okay? And that will give you an idea of your activity and eventually your specific activity. So this right here is this entire process put together into nice figures and pictures of what you see. Here we are making the homogenate. Has everybody used one of these? It's a little plunger. No? It's basically like a blender that's just not very rough, like a gentle blender, okay? And so what you would get is you'd get this surface here, it spins around. It only has a certain amount of clearance between it and the side tube. And that's going to cause certain cells to get hit and broken. And eventually you'll break all the cells without foaming it up and breaking all the proteins. Okay. What did you guys use to break your cells, by the way? I'm curious. Oh, you just mashed it in a plastic bag? Oh. Okay. Yeah, I mean, you can break some of them open that way. This would just be a more quantitative method. You'll get a much better yield. Okay, so the next thing that's going to happen is you're going to take your supernatant, you're going to spin it at low speeds, okay? 500 times G. Everybody knows what G is? Gravity? This will be for 10 minutes. You'll get a pellet and a supernatant. You can then pour the supernatant off. You'll be left with the pellet. This is the pellet right here. The first thing that normally comes off is your nucleus. Because you normally don't smash the nucleus open. And so you get nuclei coming off. There you go. Okay. You'll also get things like micelles and stuff pretty regularly, depending on your sample. Okay. Anybody know what a micelle is? It's how you transport like insoluble stuff in the blood or in the cytoplasm. Okay, so the next thing that you're going to do is you're going to spin it at a much faster speed. Now notice, by the way, this would be what we can do in the organic lab, okay? We can't go up to these speeds up here. And in fact, I don't think you guys can do this down here, downstairs. I'd have to check, but I bet you can't. You're only going here, okay? Because the ones that go up here can like dent metal walls. And so if they failed, they'd kill everybody in the downstairs. Yeah. We have no metal in the walls. They would just take out, Dr. Nelson. So probably not. I hope not. So the next thing that's going to happen is we do it 10,000 times gravity for 20 minutes. And that's typically going to remove the vast majority of your mitochondrial fractions, okay? So the mitochondria are a bit lighter, and so now they'll start falling out, right? By the way, if you just let it sit for long enough, this stuff would actually fall out, but at that point, you're going to have rotting, and yeah, this isn't going to work out for you. So the next thing that's going to happen is you centrifuge it at 100,000 times gravity for 1 hour. This is going to give you your pellet that's going to have things like your microsomal fractions. Okay? Everybody knows the microsome in the cell? Kinda. Okay. We'll have a part where we go more over more of this, but anyways. It's a structure within the cell. Now, at this point, you should have basically the stuff that's insoluble has mostly come out. Okay? Your cytoplasm would typically be your soluble proteins, right? Now, you can play games with this by changing your pH and just slightly changing your pHs. And it'll cause your proteins to become more or less soluble, okay? So you can play these games even more if you do what's called salting out. So salting out is the effect by which the most proteins are less soluble at high salt concentrations. As you add salt to a solution, okay, it's going to become more and more ionic. So anything that had less solubility originally is going to be, if it's not already miscible, even if it is miscible, it could start coming out of solution. For example, you can do this to isopropyl alcohol. If you add enough salt, you'll actually get the isopropyl alcohol start separating from the water, okay? And that's a miscible alcohol, right? So obviously it takes much less salt to do this for a protein, right? The salt concentration at which a protein precipitates is going to differ from one protein to the other. So this is a very experimental approach. In every protein basically that you do, even small change in the side groups, fairly small change in side groups could change how much hydrogen bonding does and thus change your salt out concentration, okay? So you have to test these for their specific reactivity. Eventually you'll figure out a procedure and hopefully it won't have to change too much. But I'll tell you what, I worked with Aaron Fenton's lab, and every single sample I got from them was different. Okay, had completely different concentrations. And this is part of why. Dialysis, proteins can be separated from small molecules, i.e.g. salts. So like if you salted stuff out, you can reduce the amount of salt in there by dialysis through a semi-permeable membrane, like a cellulose membrane with pores. Okay, that's those little, have you guys used those semi-permeable membranes? They come in like little tube things. Time off. No? Yeah. Okay. You know what a sausage looks like before it's made into sausage? It has like the little sheath tube, which looks like condoms because the original condoms were those. Anyways, yes, that's a semi-permeable membrane, and then you'd fill it with, instead of sausage, protein. Okay? It's just not, we don't normally use, pig intestine. We use cellulose membranes typically that have pores, semi-permeable pores. Actually, you can regulate how big these pores are. There's quite a bit of work that can be done there. The molecules larger than the pore diameter will actually remain inside the dialysis bag. It isn't actually necessarily the molecule itself that needs to be larger. It's how it's presented in solution that needs to be larger. And there's some interesting factors in play there. Okay? But overall, molecules larger than the pore will stay inside of the dialysis bag. Anything smaller is going to equalize with the solution around it. You can then take the solution and replace it to minimize that concentration as much as you want to do. Okay? You can also do the reverse, actually. You can cause salts to enter. And so if you want to change the salt concentration, you can actually do it this way. Or the pH, for that matter, as well. Anyways, the small molecules, again, ions, will diffuse outwards towards the lower concentration gradient, which is usually the solution you added to it on the outside of your membrane. And these are going to emerge in the solution outside the bag. You can actually separate the large stuff from the small stuff if you want by doing this, by having it express outside of the dialysis bag. So there's kind of interesting games you can play. So this is going to be, notice by the way, these are very similar to cell membranes. This is how a cell membrane works as well. Okay. So the dialysis is going to separate your proteins from your smaller molecules. This is the most common way you do this. This is a very common way to get rid of the small molecules because they're very difficult to get rid of, as you could see from spinning it down. They're basically impossible. Okay? And salting out the protein can sometimes damage it. So this is a method that's much more gentle. Okay? All right. And so you have here a dialysis bag with your protein supernatant solution you got before. It's going to be the concentrated solution. We put in a buffer around it so it doesn't change the pH considerably. If you don't use a buffer and use DI water, the pH will change with it. Okay? And which could mean you destroy your protein. At equilibrium, you're going to end up with the same concentrations of anything that can pass through that membrane. Okay? Anybody have any questions? No? Okay. Okay, let's talk a bit about gel filtration chromatography. This is the molecular exclusion chromatography, by the way. This is going to separate proteins based on the basis of size, specifically how well they can go through the gel. Okay? Which isn't actually necessarily their straight chain size. All right? There's a bit of a difference there. Or their molecular weight, I should say, is even bigger. Like, you can have something circular that's very compact, that's very high molecular weight. You can have something that's really stretched out, that's much lower molecular weight. And the stretched out thing will tumble through solution, right? And so it goes slower. Okay? So a column is going to be filled with porous beads. The sample is then applied to the top of your column. Notice we're doing something very similar to this this next few weeks, just with pigments instead of proteins. Wait, I think actually some of the pigments are proteins, if I remember. Never mind. We're doing something very similar to this, period. Anyways, we aren't using porous beads, though. There's the difference. So when a protein solution passes over the beads, the large proteins cannot enter the beads, and they'll exit the column first. So this is a way of, this is actually how like the N95 masks works against COVID, by the way, in case you're curious, is that the COVID virus is small enough it can get lost inside the pores, and so it passed through much slower than the normal air. Okay? But yeah, so what's happening here is it's actually kind of a reverse of what you might think. So the proteins that can't get into the pores take a straight route and go faster, right? The stuff that can actually go into the pores will then slow down, okay? This is very different than what we're doing this week. This is why this is different, because we're not using these beads with the pores, okay? So it's kind of the reverse with what we do. The small proteins can actually enter the beads and will exit the column last. And this is actually what it looks like. You can see here we have our protein sample. We loaded it on the column here. We then have our molecular extrusion gel. These molecular extrusion gels are actually pretty simple resin plastic beads, basically, that they are made under very stringent conditions, okay? And so they'll have basically a maze within them, a labyrinth, set to a certain size. And more often than not, they just test them to see what size they are. They don't know that if we do this exact process, we would have gotten that size. It's one of those places where we actually usually don't even know what we're doing. But it works. So anyways, you put a sample in. What's going to then happen as you drip your buffer solution through, you're going to see the different states separate. Oftentimes, these are not visible, except many times what you can do is you can put a black light to it, a UV lamp, and you'll cause these to fluoresce, okay? It won't necessarily be that each protein you want to separate is a different color, but you'll see different bands coming off, okay? All right, so what's then going to happen is you're going to get a bunch of samples out. You want to pretty much rotate these into fractions, okay? 5 test tubes will not be enough usually. You'll usually use a bunch, okay? And then you'll separate them into different fractions depending on the time. These fractions then will have concentrations of different proteins, okay? Depending on the size. The bigger ones will come off first, and that's what we're seeing here. And then we'll get another fraction, probably a clear, nothing. And then we'll get the green probably, and then another fraction probably again because there's a gap. And then we'll get another fraction, right, which has the next one. Everybody see that okay? Anybody get confused or lost? No. Okay, so the ion exchange chromatography, this is going to separate proteins based on charge. By the way, anybody ever been into the general chemistry lab? You've all been there, right? Did you see like the large column up there next to the DI water tub? Okay, that's an ion exchange chromatography column. Okay, literally we're doing the same thing. We're just taking the ions out of distilled water and sticking them into that gel, right? And then we will flush it sometime later when it starts to get filled. So the ion exchange chromatography, this is going to separate proteins based on their charge. The column is going to be filled with charged beads. The sample is then applied to the top of the column. When the protein solution is passed over the beads, the proteins with the same charge as that on the column are going to exit the column very quickly because like repels like, right? So they're not going to stick to the beads. The proteins with the opposite charge, on the other hand, are going to bind to your beads. How tightly is going to depend on the exact protein, the salt concentration, the charges, based on pH and salt, right, of your protein. And so you can modulate that to quite a bit of degree. Ultimately, these are going to be released because what you'll do is you'll increase the salt concentration of your buffer that passes through the column. You can actually gradually ramp that up and actually semi-selectively release proteins as you want, okay? So you can actually get fractions off this semi-selectively rather than just time, right? This actually shows you what this looks like. So right here we see that we have some positively charged proteins at this pH. Those would have an extra, positive charge on a side chain. They're going to stick to our negatively charged beads. By the way, these beads don't exist within a vacuum. Typically what you'll have is you'll actually have like magnesium or something in here, and those ions will get released when the protein sticks and come out through here. And so you can actually then reverse it by putting in salt. The salt then sticks to your beads and your protein comes out, right? Notice the negatively overall charge, they're going to pass right through and come off first. The cation exchange chromatography is going to use negatively charged beads, and anion exchange chromatography will use the positively charged beads, as you guys all probably figured out right away. By the way, the thing that we attach these charges to, typically we just use cellulose or agarose because it's cheap, easy, disposes nicely, it's perfect basically. To make it negatively charged, we attach a carboxymethyl group, CM group, and this is the ionized form, of course, in our buffer. And this then would be the protonated form, the positively charged form, which is a diethyl amino ethyl, DEAE group. And by the way, yes, basically the methods we showed you in organic chemistry are the methods you use to do this. Yeah. It's to make those. So affinity chromatography, this is going to take advantage of the fact that some proteins have a high affinity for specific molecules that we call ligands, of course. We just talked about that, didn't we? The binding of ligands. Yeah. So remember that most proteins have some sort of binding, don't they? And so most proteins have a certain degree of affinity for a ligand. What do you think this composes of? We have beads. What do you think we attach to the beads? Yeah, something that looks like the ligand it would normally bind to, right? And we could do something a little stronger than it would normally bind to, or we can do something a little weaker than it normally binds to, depending on how easy it is to unattach, right? Yeah. So when the protein solution is then passed over the beads, the proteins with affinity for the attached group are going to be retained, of course. The bound protein is then released by passing a solution with an enriched source of the ligand to which the protein is bound through the column. And so then you're going to exchange the ligand that's bound, right? With the free-flowing ligand instead of the bead-bound ligand. Okay? Did I lose anybody there? Okay. These ones are amazingly selective. You can get an incredible amount of specificity and even target like specific variants of hemoglobins and stuff, specific variants of the protein that have a slightly higher binding and lower binding. You can do a lot with this, but it takes some work, okay? It can take years to develop a specific binding for a specific protein on one of these. It's quite a challenging job. These right here are actually glucose. So glucose attachment proteins. We have a glucose that's attached to our beads. Then in this case, 2 of them. So what will happen then is our protein will then attach to our glucoses here, and those will then get stuck. When we want to release them after everything else went through, we'll then just add a solution of glucose that has a pretty high concentration of glucose. This will cause the glucoses to bind to those proteins and come off. Notice, by the way, you never actually get all of it off and all of it on, okay? These are all the equilibriums we just talked about. That KD determines how strongly this binds on here, okay? The nice thing being that because you use the free ligand here, as long as you use a high enough concentration, you're getting it off, or at least the vast majority off, okay? High performance liquid chromatography. This is a pain in the fucking ass to keep their system running, okay? But as a user, it's wonderful. As long as you have somebody that knows how to keep it running, right? Good God, the amount of work you have to do to keep these fucking things running. Okay? There was $1 million system at UMKC. They threw it away because the person that maintained it left. And they couldn't find anybody else for like 10 years. Yeah. The resolving power of any chromatographic technique is going to be related to the number of potential sites of interaction between the protein and the column beads. The less interactions you can have, the less it's going to be able to interact, right? The less it's going to be able to resolve slight differences. Okay? So for example, the size differences, we had fairly low resolving power, right? Because there isn't a lot of interaction. Is it that big or not? Okay? The charge differences, again, we have fairly low resolving power individually, right? The affinity chromatography has very high resolving power. But there's still a fair number of glucoses, right? So again, the more possible interactions, the more resolving power you can maintain. Okay? So very fine beads allow more interactions and thus greater resolving power. But the problem is, if we have, everybody's taken like a vase and seen it with a vase with like marbles in it or rocks in it. Water flows fast, right? Okay. What happens if the gaps are very small? You fill the vase with like soil. It goes much slower, right? So whenever you're doing a separation, you're always working against time, right? If the separation takes 20 years to perform, are you doing it? No. No. That's Fiji, by the way. Takes 20 years to perform separation, but it works really well. You know Fiji water? Yeah. So you're always got to run that happy medium, right? So at certain points, having more interactions increases your time so much that you just can't do it anymore. But how can you get things to move faster through that? You'll do it in the lab. I'll show you how to do it. You put pressure, right? Okay? That's how you do filtration, isn't it? Gravity filtration takes like 3 hours, right? We do the vacuum filtration by putting pressure against it. We can get it done in like, 10 minutes. Okay? And so high performance, or sometimes people say high pressure, but high performance liquid chromatography, HPLC, is going to use very fine beads in the column, but it'll have to use pressure to move the liquid through the sample to get it done in a reasonable time. If you have one of these maintained and properly set up, you can take separations that would take weeks and do them in a matter of 10 minutes. Okay? This leads to sharper separation between protein and more rapid separations. Really, really drastic. We're done time? Okay. Thank you very much for letting me know. We'll start up here next time. Not even close to finished.